So in today's video, we're going to talk about simple diffusion. So simple diffusion, we're going from high to low concentration. Also, it's a passive process. It does not require energy. It does not require ATP, right? So two equally sized aqueous compartments separated by an artificial lipid membrane, so that this is the membrane, that only allows urea to pass. At time T0, compartment A contains 5 millimoles urea, and compartment B contains 1 millimole urea. The temperature is 27 Celsius degrees. So we're going from A to B, right? The concentration is bigger in this compartment, and therefore by simple diffusion, the concentration will get balanced by shifting some of the molecules over to this compartment, compartment B here, okay? So write down the formula for the passive urea net flux and indicate its direction. Just so you guys understand what net flux is. Net flux in the context of diffusion refers to the rate of movement of a substance across a given area over a certain period of time. So here we have the area, right? Suppose you have, let's say, 10 particles moving from left to right and from left to right, and from right to left, you have 3 particles, so that will give you 10 minus 7, so it give you a net flux of 7, okay? So flux is basically just particles or moles of something moving over a certain period of time through an area, okay? Typically, we're talking about 1 second, right? And J is called simple flux. So let's get on to the task here. And just so you might understand, urea is a waste product formed in the liver during protein metabolism. So in the context of diffusion, urea can diffuse across cell membranes through the cell membrane, for example, through passive transport, simple diffusion. Okay, so let's try and solve this equation. So we can utilize a Ficks first law, and this is the simplified version of Ficks first law, where Jx represents the flux or rate of diffusion of a substance across a membrane in the x direction. So from this direction to this direction, right? Or from this compartment to this compartment, from A to B. We have Px, which represents the permeability coefficient of the membrane, right? Which, of course, varies. And then we have x0, so represents the concentration of the substance outside the membrane, and this the concentration of the substance inside the membrane. Of course, since we're talking about urea, x is urea, and this is the equation given. And if you want to indicate its direction, it goes from this direction, so it goes from A to B, right? To put it lightly. Now let's try to solve B here. Calculate the energy released by transporting 1 millimole of urea across the membrane at T0. So here we have a couple of equations, right? The work done in the inward transport of substance X can be calculated using this formula. The electrochemical potential difference between the inside and outside of the membrane for substance X can be used calculating this formula, or excuse me, can be found via this formula. And finally, we have this formula, which is the one I'll be utilizing. So the work W to move the uncharged substance over a membrane is given by this formula, okay? And the unit is given joules over moles. Of course, R is the gas constant, T is the temperature, right? And X is the so inside the membrane and outside the membrane, okay? So inside the membrane we have 1 millimole, and outside we have 5 millimoles, okay? The R constant is given as this one, right? You can find it using Google. The temperature is 27 Celsius degrees, so you just simply add this number here, 273.15, and that gives you the temperature in Kelvin. And we insert the values into the formula, and we'll quickly find the result, so which is 4,000 joules over moles. right? Or 4 joules over millimoles, which gets released. Don't mind that it's a negative here. The reason why it's negative is simply because we're releasing it, right? So 4 joules over millimoles get released by transporting 1 millimole over the membrane to T0. Okay, so now we've solved this question. And what about C here? What happens to the released energy? Okay, think about it. Well, what happens is when we're talking about passive transport, such as diffusion, the movement occurs spontaneously down the concentration gradient. And instead, the energy associated with the concentration gradient drives the movement of molecules. Therefore, there wouldn't be energy released or consumed in the process of passive diffusion itself. So this leads me to saying that the released energy is typically dissipated as heat into the surroundings. So when urea molecules moves down the concentration gradient across the membrane, energy is released due to the decrease in potential energy associated with the concentration difference. So this energy is usually converted into thermal energy, which is increasing the overall temperature of the system, of this system right here, and also the surroundings, right? So what happens to the released energy is heat into the surroundings. And this thereby also increases the potential energy. Potential energy. Now they ask you what will be the concentration of urea in the two compartments when equilibrium is reached, and what principles have you and which principles have you used during the calculation? This is very simple. Well, what ends up happening is in equilibrium, of course, we'll have uh, the same amount of urea in both compartments, right? So you simply need to add this one with this one, so the concentration here and here, you add them together and divide it by the two choices. That gives you 3, okay? So if the equilibrium concentration of urea in both compartments is indeed 3, it suggests that the system has reached a point where the concentration gradient has equalized and there is no net movement of urea across the membrane. Okay? And the principle they probably want me to mention is the principle of conserving mass, right? So in equilibrium, 3 millimoles in compartment A and 3 millimoles compartment B.